Hello, my name is Lance Carriere and my presentation is on transmission electron microscopy. Before the invention of the transmission electron microscope, the only method for obtaining magnified images of small samples was through the use of an optical microscope. These are the microscopes that we're all already familiar with, making use of the witchcraft known as bent glass to manipulate light and provide a generally larger image of whatever specimen one inserts into the apparatus. As one would expect, this method produces an image based on how the light one uses in the microscope interacts with the specimen. Due to the fact that the medium used in this case is light, the ideal or maximum resolution one could hope to achieve with this method is limited in part by the wavelength of the light used. In theory, the maximum resolution of a light-based microscope can be obtained via the equation shown here. The variable d is the maximum resolution, lambda is the wavelength of the photons used to examine the specimen, Na is the numerical aperture of the system, and n is the index of refraction of the medium in which the lens operates. The spectrum of visible light ranges from wavelengths of roughly 400 to 700 nanometers. In calculating the resolution, we will assume the wavelength used is 550 nanometers. By plugging this into the resolution equation, the highest value of d one can feasibly achieve is around 200 nanometers. This was a fairly aggravating roadblock, as this essentially said that the optical microscope could not view things such as viruses, ribosomes, and anything else less than 200 nanometers in length. Microscopes which utilized ultraviolet light, whose wavelength is less than that of visible light, were developed in order to improve the available resolution. Unfortunately, the improvement to the resolution was only roughly by a factor of 2. Additionally, these types of microscopes were more expensive to manufacture, as the typical glass lenses needed to be replaced with quartz in order for UV light to be transmitted through them. Other mediums were utilized instead of air, such as oil, which would increase the index of refraction, but the improvement was minuscule. By using electrons instead of photons, the wavelength in the numerator can be replaced with the expression for the de Broglie wavelength of the electron, shown here. A correction must be added to this equation to account for relativistic effects as, in a transmission electron microscope, electrons are accelerated to nearly the speed of light, resulting in the final equation here. It had been known for many years that the electron beams could be warped through the application of a magnetic field, but in 1926, Dr. Hans Busch proposed that cathode rays, that is to say electron beams, could be focused by magnetic fields in the same way that light can be focused by transparent lenses. Furthermore, he showed that the lensmaker's equation, shown here, could be applied to electrons as well under certain conditions. In September of 1933, the first instance of exceeding the maximum magnification possible with light microscopy was achieved. Cotton fibers were briefly imaged by the apparatus before being destroyed by the electron beam. The microscope used, created by Ernst Ruska, was the first electron microscope with the ability to image specimens inserted into the device. Shown here is a diagram of the internal structure of a transmission electron microscope. The electron beam lenses are actually variable electromagnets which, as one would expect, produce magnetic fields. Using these, one can adjust the position and focus of the electron beam to interact with the sample as needed. In addition to the magnetic fields, electrostatic fields are also used, which deflect electrons at a constant angle as opposed to the varying angle of deflection achieved via use of a magnetic field. The focusing devices in the transmission electron microscope are designed to mimic the effects of optical lenses. The majority of these lenses do so by utilizing electromagnetic coils to generate a convex lens. Because of the high currents necessary to generate strong enough magnetic fields, cooling pipes and a thermal distributor are required to maintain the integrity of the device. The electron source is usually one of two substances, either a titanium filament or a lanthanum hexaboride crystal. In the case of the tungsten, the filament is shaped into either a hairpin-like filament or a small spike-shaped filament, as shown here. For the lanthanum hexaboride, a small crystal is mounted on a slab of insulation which is then heated to emit electrons. In either case, the substance is connected to a high-voltage power source of 100 to 300 kilovolts, and electrons are admitted into the vacuum via thermionic or field electron emission. The electron gun is formed from several components: the filament, a biasing circuit, a Wenelt cap, and an extraction anode. By connecting the filament to the negative component power cable, electrons can be pumped from the electron gun to the anode plate and TEM column, thus completing the circuit. The gun is designed to create a beam of electrons exiting from the assembly at some given angle, known as the gun divergence semi-angle. The thermionic emission current density J can be related to the work function of the emitting material by Richardson's law shown here. The variable A is the Richardson's constant. phi is the work function, and T is the temperature of the material. In order to maximize the mean free path of the electrons as they travel down the apparatus, the entire microscope needs to be evacuated to a pressure of around 10 to the negative 4th pascals. This is achieved by first utilizing either a rotary vane pump or diaphragm pumps to achieve a low vacuum. Then, a turbomolecular or diffusion pump is used to create the high vacuum necessary for proper operation. When using a higher voltage, the pressure inside the electron microscope must be further reduced to 10 to the negative 7th to 10 to the negative 9th pascals. This is to prevent electricity from arcing from the filament or the crystal to the ground. We then come down to look at the specimen stage. Here, samples are placed upon a 3.05 mm grid typically made out of copper. Because it's intended for electrons to pass through it while interacting with it as little as possible, the thickness of the grid ranges from a few micrometers to 100 micrometers. In accordance with the name, the process of transmission electron microscopy involves producing an image via passing accelerated electrons through the specimen and onto a fluorescent screen. The image data is collected here based upon how the electrons interacted with the substance, in much the same way as X-ray imaging. In order to accomplish sufficient electron transmission, the specimen needs to have a thickness on the order of nanometers. This is to make sure that enough electrons interact with the specimen as well as ensure that enough electrons will pass through it. One way in which this is achieved is by encasing the sample in resin, then cutting it with a specialized diamond blade to create ultra-thin sections of around 70 to 350 nanometers in thickness. The resin is used in order to help prevent deformation or destruction of the sample during the sectioning process. Another process exists called mechanical milling, wherein a sample is mechanically polished down until it is of the desired thickness. As a final stage of polishing, a diamond or cubic boron nitride polishing compound can be used to further remove any scratches that may cause a non-uniform thickness in the specimen. Chemicals such as acids can also be used to wear a sample down until it is of the proper thickness. This process, not surprisingly, is called chemical milling. A third process exists, which is called ion etching. In this process, an inert gas is passed through an electric field in order to generate a plasma stream, which is then directed at the surface of the specimen. The typical rate of progress that this method produces is wearing the specimen down by a few micrometers per hour. Because of this slow rate, this method is most effective in finally polishing a specimen after using one of the methods previously mentioned. For biological samples, sometimes staining the specimen will produce a more detailed image. Compounds of heavy metals such as osmium, lead, uranium, or gold can be utilized in order to more effectively absorb or deflect the electrons being fired at the sample. The device into which the sample is inserted is adjustable in order to achieve the optimal angle and position for imaging. Translation is available in the X, Y, and Z directions, and roughly 1 degree of rotation is possible for the sample. These systems are usually operated via outside devices such as analog sticks or trackballs.